Hi, if you're joining us later, catch you up a little bit. So the nice integer coordinate points are going to be the powers of 2, right? I didn't label 0, 1 here. So as this thing goes to the right, with any behavior going that direction or positive infinity, what is it doing? Increasing, growing, right? Pointing up, right? Grows without bound. And like if you look at what these do, it's going to happen pretty quickly because 16, 32, 64, like you're doubling at each step, right? So that end is pointing up to the right. What about going this way? What happens for negative values? Say it again. Okay. Yeah, it looks like it's sort of flattening out, right? It looks like it's doing a horizontal asymptote kind of thing. Like it's pointing toward the x-axis. Let's take some negative values and plug them in. Just to get a feel for what's going on. So if x is -1, 2 raised to the x would be 2 to the -1 power, right? But what does a negative power do? Flips it, right? Negative exponents are reciprocals, so 2 to the -1 would be the same thing as 1 over 2. Okay, so apparently this point would be -1, 1/2. Oh, gosh. Okay. What if you plug in -2? 2 to the -2 would be the reciprocal of 2 squared, so 1/4. This would be 1/8, 1/16, and so on, right? Okay, so going, looking at like the y-axis is kind of the center. If we go to the right, we get positive powers of 2, right? 2, 4, 8, 16, right? All this stuff between them is there too, right? Because it's a continuous function, it's connected. But the like nice points that we would, draw by hand would be the powers of 2, 2, 4, 8, 16. If I go to the left from the y-axis, well, I get the reciprocals of those, right? Because they're negative powers flip things upside down. So 1/2, 1/4, 1/8, 1/16, so on, right? Okay, so this way, it's increasing to the right, growing without bound. Gets, pretty steep pretty quick, right? It never turns vertical. It does, keep going forever, kind of up and to the right, but it does it like really quickly, right? This grows a lot faster than anything that we've looked at before. But to the left, what it does is, because it's the reciprocal of that, it does a horizontal asymptote kind of thing, right? It's always sort of sitting just above the axis because, look at what's going to happen, right? It's 1 over, well, the next biggest power of 2, right? So that's always positive. But it can be, sort of as small as you want it to be, just like we saw with some of the rational stuff. So there's a horizontal asymptote here. And again, what that horizontal asymptote shows you is, in behavior, the thing that is kind of different here than the stuff that we just finished looking at is that the asymptote only tells us about sort of one side of the thing rather than both, right? The rational stuff, they sort of flattened out both directions and kind of leveled into that horizontal asymptote. Exponentials is just like one side, right? So it's, it's still a horizontal asymptote. We still talk about it the same way. It's just that what it shows you is only like half of the graph of the thing. So exponentials always kind of look something like that, or flip. We'll get to that in a second, but they always kind of look something like that. Where if I'm going to talk about the end behavior, it's like different if you mean to the left or to the right. One end is sort of growing, the other end is sort of dying out. This is an example of what we call exponential growth. Because over time it's increasing. Okay, so what about the domain and range and stuff for this? Yep. 0 to infinity, because it's in the upper half. And what should we do with 0? Include or not? Does it ever actually get there? No, because it's always sort of just above, right? Because no matter, negative 1,000 or something, right? 2 to the 1,000 power is a big number, but it's the reciprocal of that, right? 1 over it's still positive, right? You're never actually going to reach 0, which means there are no x-intercepts. There's a y-intercept at 0, 1, and again, there's that horizontal asymptote. At y equals 0. Okay, does anybody have any questions about it so far? We're okay with kind of how that works in sort of like an abstract, like, okay, here's the graph sort of sense. All right, so let's think about an example of where this kind of thing happens, because this is actually something that applies and touches on a whole bunch of stuff across a whole bunch of different disciplines and things, like everything from population growth to like financial stuff is modeled by exponentials. So it's all over the place. So let's take a look at a couple of examples, and I can remember how to do that. Here we go. We missed spooky season by 1 day, but it's all right. So I need to make this scary. Zombie apocalypse. It's a hard word to spell. There you go. Okay, so so you know the drill, right? Like somebody turns into a zombie, and the zombie goes and bites other people, and then they turn into zombies. And then there are more zombies, and things go sideways, and like then everything's on fire, and like there's trash blowing in the streets, and like we're right. Everybody's good. Okay, so day 1, there is a single zombie who gets out and does his thing, and nobody knows how to stop it and whatever. Every day at 3 o'clock. Each zombie infects 1 more person. And that person turns into a zombie, and then the next day they're a zombie too, right? Okay, so day 1, there's 1 zombie. How many are there on day 2? At 3 o'clock. When this new person who got infected turns into a zombie, how many are there? 2, right? Because the 1 zombie from the day before went out and bit somebody, and now there's 2. Okay. The next day. Now there are 2 zombies. They each go out and infect 1 person, right? Okay. All right, y'all fill in the rest of the first week then. So what's the pattern? How do we get from one day to the next? Multiply by 2, right? Times 2, times 2, times 2, times 2, times 2, times 2. What's happening is that the number of zombies is doubled, right? One day to the next doubles. Okay, well, you've done stuff that works in that same kind of way, but with addition instead of multiplication, right? Those are linear functions. When you do the slope thing to draw a line, you do the, rise over run, stair steppy kind of thing to plot 120. That's doing this, but with addition instead of multiplication, right? Okay, so now when we look at exponentials, we're talking about, that same idea that there's sort of a constant rate of change, only instead of adding, the way that you use that growth rate is multiplication. Okay, well, if what we're doing is multiplying by 2 over and over again, then hopefully you can see how, writing 2 times 2 times 2 times 2 over and over and over again is kind of a drag. So we use a shorthand, right? And a shorthand for multiplying a whole bunch of times is a power, right? An exponent. So this is just 2 to the x again, right? I've shifted the thing because we started counting on day 1, but I don't worry about that part so much. You start to see what happens here. We went from 1 to 64 in the span of a week, right? How can we figure out what happens after another week without just, punching in times 2 a whole bunch of times? Now, what if I want to figure out what day 14 looks like without, just having to manually calculate the thing out? This is where the function part would come in, right? If x is the number of days and y is the number of zombies, then this is 2 to the x. And we did one little thing when we shifted it. It's 2 to the x minus 1, right? Because I shifted the whole thing to the right by 1, basically. So that if x is 1, I get 1 minus 1, so 2 to the 0. So 1, if x is 2, I get 2 to the first is 2, right? So what would day 14 look like? 2 to the 14 minus 1, so 2 to the 13. Somebody tell me what 2 to the 13th is real quick. How much? 8192. I imagine that you had already done that, but it looked like you just knew that off the top of your head. And that was cool. Just no big deal. Let's do like that the episode of The Office where Michael was talking about I can't remember, it's the budget surplus thing, and anyway, I'm enjoying the moment. 2 to the 13, 8,192. Okay, so we went pretty quick from 64 to that, right? Let's jump ahead a little bit further. How about after a month? Malaysia, 2 to the 29th. No, you don't need a calculator. You can just do it, right? I don't have a calculator. 5, 3, 6, 8. One, two. Okay. Oh, half a billion. And what happens the next day? You double that again, right? And now you're really freaked out about the zombie apocalypse thing, right? Oh, that's how it happens that fast. I mean, we went from 1 to 500,000, and in 2 more days, it's going to be 2 billion. And then, like, 2 more days after that, like, that's curtains, right? Because there's like 8 billion people in the world or something. So you see why, I've said several times, like, these things grow really fast. These things grow really fast, right? Okay. So that's, exponential growth. That's a thing that is doubling over time. That's why, have you guys ever heard the thing where, it's like, would you rather have $1 million, or instead, what if I took a chessboard and put a penny on the first square, and then the next day put 2 pennies, and then the next day put 4 pennies on the next one? Have you ever heard this thing? No? Okay. Well, let's just do it real quick because I feel like it. So 64, right? I didn't draw the thing right, but 64 squares. You put 1 penny on the first one. The next day you put 2 pennies on the second one. The next day you put 2, 3, 4. So you double it each day, right? So that would be, because it's doubling, right? That's the way that the thing is changing, is doubling. So that's 2 to the x, right? That handles the doubling part. To handle the fact that it's starting with 1 cent, you just take that and multiply by 1 cent, right? 0.01. So day 1, 1 cent. So again, we need to do like a shift thing because we start counting at 1. So that would do it. So day 1, you get 2 to the 0, which is 1 times 1 cent. Day 2, you get 2 to the first times 0.01, so 2 cents. Somebody do that when x is 64. So your calculator does the thing where it gives it back to you in scientific notation, right? 9.2, a bunch of other decimal stuff, E16. That means times 10 to the 16th. So that's 9 with 16 zeros after, right? Or, they're not zeros, but that's it. What is that? Well, billion is 9, so trillion, so quadrillion, so 9 quintillion? They're pennies, but that makes it $90 quadrillion or something, right? That's good. I'll take that one, please. Right? Okay. So the point, though, for all of this is just that, like, it all grows really fast. Okay, what if we tweak things a little bit and do the same stuff, but now each of the zombies goes out and infects 2 more people instead of 1? What's going to change? So we go from 1 to 3 to 9 to 27. And so on. Times 3 instead of times 2, right? Tripling instead of doubling. What that does for the function is, instead of the base being 2, because what the base does is show you like what the growth pattern is, right? What the growth rate is. So instead of the base being 2, it'd be 3. Okay, well, graph, we know what y equals 2 to the x looks like. Graph y equals 3 to the x. What's different? What's similar? same overall shape, lives in the same place, basically, right? Does the same kind of thing. So domain and range and intercepts and the horizontal asymptote and all that kind of stuff is going to be the same, right? What's different? It's steeper. Slope is the right idea. Maybe air quotes around slope because it's not a straight line, so it's not slope in the the normal sense that we know the word slope to mean, but that's the right idea. The growth rate is faster, so the thing is steeper. So again, if I look at y-axis being the center, that way everything happens faster, right? It grows faster. You know, now instead of doubling, it's going to triple. So the numbers are going to be even, more aggressive or whatever. And this way, two to the x, three to the x. This way, it's also happening faster, right? It's just that this way we're talking about it sort of falling off or getting like closer into the x-axis, but it's getting there faster because the values are smaller, right? So it sits underneath. So they cross at the same point because anything to the 0 is 1, right? But everything happens faster. So what do you think would happen if the base was, I don't know, 5 instead of 3? Even more faster, right? Okay, cool. So the bigger that base value, because again, the base is like the growth rate. That's how it changes. That's what you're multiplying by. Bigger that value is, the faster things are going to happen. Similarly, smaller that value is, the slower things would happen, right? So if I looked at like 1.5 raised to the x, same overall shape, lives in the same place. It's just kind of slower, wider, like lazier version of the same graph, right? Everything takes a little longer. Okay, cool. How about another quick example of a thing that we know pretty well, or probably? Here is the basketball bracket, right? Okay, well, first, let's forget about the play-in game thing. Nobody cares about that anyway. How does the tournament work? Or any kind of single elimination tournament? Do it. Win in advance, lose and go home, right? So specifically this one, 64 teams get invited. They play head-to-head. Winner advances, loser goes home. So you start with 64 teams. How many are there in the next round? 32, right? Half as many. So the way this bracket's laid out, we're kind of like working from the outside in, but round 1, which is this outside stuff, we've got 64 teams. Then round 2, there's 32. Then Sweet 16, 8, 4, 2, and then eventually 1 champion, right? Okay. Well, this is the same kind of pattern, right? Only instead of doubling as we like progress, right? If I looked at it and worked kind of from the inside out, well, then I'd be doubling, right? 1, 2, 4, 8. We're working from the outside in though. So what's happening as you go along here? Let's say you got half as many, right? So it's still, sort of 2 is still kind of the pattern. It's just that instead of multiplying by 2, you're dividing by 2. Or another way to say that would be you're multiplying by half. So half as many in the next round. So our growth rate, I'm going to put air quotes in that because it's, not exactly like growing, like, getting bigger over time, but So we could use something like, and again, we'd have to, sort of adjust some things, but something like 1/2 to the x, or another way to write 1/2 to the x is 2 to the negative x. Well, think about what putting a negative sign in the inside part of a function does. That reflects things this way, right? So what does that look like? There's 2 to the x. So 2 to the x in green, right? That's growth over time, right? If I think about moving left to right as being like moving forward in time, that's growing. In purple, 1/2 to the x, base 1/2, that's what the word we'll use is decay, right? Instead of having more stuff as time goes by, you have less stuff, right? Like the tournament where you've got half as many teams after each round, or another example that we'll look at later on is like radioactive decay. Like radioactive stuff is dangerous because it breaks down and sends all these particles flying off into the area around it and stuff. The way that works is the same kind of thing. Like the amount of radioactivity breaks down over time. But it's the same basic shape. It's just facing the other way, right? Domain and range and intercepts and asymptotes and all that stuff. Is that any of that change? No. If I'm describing the behavior or what it does, over time, for the green one, the growth, the 2 to the x, I would say like that way it's increasing, that way it's sort of decreasing, leveling off, right? Well, for the decay thing, I got to switch my directions, but it's doing the same thing otherwise, right? So domain and range and all that stuff, none of that changes. So basically, this is what happens for an exponential with base b. And b is always going to be something positive because if it's negative, weird stuff happens. It's the whole thing. So the base is always positive. Everything kind of falls into two categories. Either we have something that's growing over time, or we have something that's decaying over time. But in either case, domain, range, intercepts, asymptote, the way it behaves, all that kind of stuff is the same. It's just a question of, is it increasing or is it decreasing? And the only thing that, whether it like which case we're in, which thing it kind of falls into, is the size of the base. So if the base is bigger than 1, we end up with a thing that grows over time. If the base is smaller than 1, we end up with a thing that decays over time. And again, base is always positive, so between 0 and 1, right? The size of the base affects how steep it is, right? So if the base is 2, it's going to look, maybe like that. If the base is 10, it's going to look like the same thing, but kind of faster, right? Steeper. Other than that, though, it doesn't change anything. Domain, range, intercept, asymptote, all that stuff stays the same in either case. And the same thing is true for decay. If the base is a half, maybe it looks like that. If the base is a fourth or something, well, it's going to do the same thing, but just kind of steeper, right? It's going to be like closer in to the axes, but the same basic shape. Okay. So first thing that we're going to want to like train ourselves to think about when we look at an exponential, whether that's some kind of function that we're dealing with, or something that comes up in an application or a word problem, or even something that we see in like an equation that we're trying to solve. Probably the first thing you want to think about is like, does this look like this, or does this look like this? Right? And like I mean, you know me at this point, I'm going to do this a lot. I think it's a good idea if you do too, but because that's going to tell us some stuff about how the thing behaves, right? I'm doing my hands right. Yes. Okay.
growth, decay. I'm doing those. Okay, sorry, I'm facing a different direction than all of you are moment. It happens sometimes. I get really confused about my left and my right. Doesn't matter. You don't. It's fine. I'll work it out. Don't worry about it. I very rarely try to drive on the wrong side of the road. So, yeah, good. Okay.
Great. Okay, so growth and decay. Now, there's one thing about all of the, like the zombie apocalypse example thing, the tournament. There's one thing about that that's all like a little bit artificial, maybe, like especially the zombie thing, right? The first thing I said there in kind of setting the problem up was that, okay, we start with a zombie, and every day at 3 o'clock, a zombie goes out and bites somebody and they turn into another zombie, right? Like that's probably not how they operate. I don't know. They're fictional. So like maybe it would be, but like it feels weird, right? I also said that this stuff really comes up all over the place in modeling population growth and stuff like that. So if you look at, if you look at even like census data for the last 300 years or something, it's going to roughly kind of fit an exponential. It's not as like even irregular, but kind of generally it fits that same kind of pattern. But the part about it like happening at the same time, like that's weird. It's weird to count time discretely like this, where we just sort of jump from one to the next, right? And if we're talking about something like an actual population growing, like the number of fish in the lake or whatever, or bacteria in a culture or anything like that, it's weird to put that artificial sort of constraint on it about like we're going to count time in sort of discrete chunks like that. So what happens, for reasons that we're not going to get into any further detail about, is that to really model this stuff, what we usually use is something that we call the natural exponential. Basically, the difference is that instead of assuming that it doubles from one day to the next, right, or triples or whatever, we say like, okay, well, this thing is growing all the time, right? The bacteria in the petri dish are growing all the time. Here's how we model it. We end up with this thing that we call the natural base, which is E. So if you look at your calculator, there's somewhere on the left-hand side, there's an E button in Desmos or whatever. This lowercase e, it knows that that's what E is. And what E to the X looks like is this. So what do you know about this new mysterious number E, just by looking at that graph? Is this growing or decaying? Growing. Well, if it's growing, then E must be bigger than 1. One is the cutoff. 1's the break point. Because remember, what we're doing is multiplying by whatever that base is. You multiply by something bigger than 1, you get back an answer that's bigger. If you multiply by something smaller than 1, you get back an answer that's small. Right? That's why 1 is sort of the cutoff. E's got to be bigger than 1, right? Okay, now punch in E to the first. You actually get like the value of E. E is about 2.7. It's transcendental. So, like pi, it's a special number that means special things that we need calculus to really, explain like what it does, where it comes from. But it's one of these, infinite decimal, non-repeating things. For our purposes, all we really need to know is that it's bigger than 1. Maybe that it's between 2 and 3. Like you're not going to need to, know this number. If there's a calculation that you need using E, you're just going to punch it into a calculator anyway, right? But it is helpful to know that because it's, a little bit bigger than 2, it's going to be a thing that's growing over time. And if I graphed it with like 2 to the X and 3 to the X, it would kind of sandwich right in between, right? That means domain, range, all that kind of stuff works the same here as it does for the others, right? So domain, negative infinity to infinity, range 0 to infinity. There's a y-intercept at 0, 1. There's a horizontal asymptote at y equals 0. And the thing's growing over time. And I already told you what the value of E is because I forgot that I had that question there. Okay. I am going to jump a little bit and talk about a couple of interesting applications of this stuff that are things that we should care about. And if you don't care about them already, you will someday because it'll either work in your favor or against you or maybe both. So compound interest. This is a simplified version a little bit of how investments and loans and stuff like that work. So basically what we're assuming is that if I take some money and put it in the bank, well, the bank wants to hang on to my money so that they can use my money to give other people loans so that they can charge them interest so that they can make money, right? There are no free lunches, right? Everybody's, looking out for number one. But so the reason the bank pays you interest on, your savings account or your investment or whatever is because they're going to use your money to loan out to other people, and they're going to charge them more interest than they're paying you, right? Like that's how the thing works. And if you borrow money from somebody, they charge you interest because, well, they're letting you use their money for a while, right? And the thing that we want to be, cautious and wary of is making sure that we are, shepherding the things that God has blessed us with well, and not getting, taken for a ride. So things like, short-term loans, payday loans, that kind of stuff. Those people are bloodthirsty. They are out to get you 100%. And if you look at the fine print, it's always like, oh, you're like 2,000%. Like, just kidding. Things happen, like you got to survive, whatever, but be aware of that kind of thing. What am I saying? Anyway, there are kind of two ways that we're going to look at that this works. Either we look at the compounding. When I say compounding, I mean like that's when the interest calculation happens. We look at that happening either sort of every so often, right? Like once a month or once a year or once a quarter or whatever. Or we look at it happening continuously. So we've got two formulas here that model that. If it's periodic, so any kind of like time frame associated with it, it's this. If it's continuous, it's that. This looks like a lot. We're going to talk about what all this stuff means, but we're looking at this as a function of time. So T is, like X here, right? And A is like our Y value. So all this stuff in here is the base. We're multiplying by some value here that's going to change sort of the starting point. And then again, this stuff is the, like the variable basically. It's playing the role of X. So we'll get more into, as we go along, we get more into like thinking of this as, an exponential function. For the moment, it's pretty much just going to be kind of a formula to plug stuff into. What all this stuff stands for, though, and it's all written there, but I'm just going to kind of highlight stuff and say it. A, that's the amount, the accrued value of the investment, right? So if I take $1,000 and put it in a savings account in the bank and it pays such and such interest rate, this is how much money I have after some time has passed, right? So that's the answer from that formula is how much you have now. P is the principal. That's what you started with, right? So if I take $1,000 and deposit it at the bank, that's P. So that's how much you put in the first place. It makes sense that that's where it shows up because you're going to take that and multiply it by this exponential thing. Well, that exponential thing is going to tell you how much it has changed. 1 is the number 1. R is the interest rate. Interest rate is always given as a percentage, so 5%. But when we use it in calculations, we need a decimal, so 0.05, right? So we got to do that conversion. N, which shows up in two different places, that's the number of times per year that the interest calculation happens. So if it says like it's compounded quarterly, that means that the bank person goes in and, you know, calculates runs the numbers 4 times a year. That would be N, and figures out how much interest they owe me and adds that onto the account, and, you know, so on. And then T is time. Time is in years because of the way everything else is set up. In the other formula, A is still the same thing, P is still the same thing, R is still the same thing, T is still the same thing, E is E, right? And we're just assuming there that the interest happens continuously. If that's what you're supposed to do, the word continuous will be in the problem somewhere, or continuously, or, you know, something like that. The way this works is that every time that interest calculation happens, like say it was 5%, I put in $1,000, they figure out what 5% of 1,000 is. That should be able to do is $50, and they add that on, right? So now I've got $1,050 in there. And then the next time the interest calculation happens, it's 5% of 1,050, which is going to be a little bit more, right? So it adds on a little bit more, and the next time it's a little bit more than that, and so this is how the thing sort of snowballs, right, and grows over time. Yeah, so there are a couple of examples there, 9, 10, 11. Try those. These are just going to be plug into the formula. So try those for Thursday, and we'll pick up there and talk about some other stuff. Y'all have a good day. I'll see you then. Excuse me.